In the previous video, we introduced how the blocks are being dispatched from the ACE to the compute unit. At this moment, we have the wavefronts waiting in the wavefronts pools to be executed. So the goal of this video is to help you understand how these instructions in the wavefront are being executed in the compute unit. Assuming right now we are in the initial status of a few wavefronts, and each wavefront has a PC register which is pointing to the instruction to be executed next. We need to introduce a component that is called instruction fetcher, and this instruction fetcher will read the PCs of all the wavefronts in the wavefront pools and to determine which one can fetch instructions from the instruction memory. So this instruction fetcher is also an arbiter that determines which wavefronts got instructions to execute. The instruction fetcher will send the request to the instruction memory system. Actually, here we have L1 instruction memory. Then the L1 instruction memory will bring the data back to the instruction fetcher, and the instruction fetcher can fill the instruction to the instruction buffer in each wavefront slot. Now we make this block smaller to make some space for some other component to execute. But let's assume all these wavefront slot has instructions ready to be executed. We first need to understand what are the components that can execute these instructions. As you may see here, there are several components that matches very well with the instruction types. We have a branch unit, which is a unit that can execute branch instructions. It's considered a scalar instruction. It's just a special type of scalar instructions. The scalar unit can execute scalar instructions and process some integer operations. It is also a memory unit that can fetch scalar data from the scalar memory system. We also have a vector memory unit. The vector memory unit can handle load and store operations and some atomic operations to interact with the vector memory system. And for most of the vector instructions, they are executed in the SIMD unit. The SIMD unit are where only the floating point or double precision floating point operations can be executed. And finally, we have the LDS unit. It can both execute the LDS instructions. It has the storage that stores the data in the local data share memory. So we need to have one component that is an instruction issuer or instruction arbiter that between the wavefront pool and the execution unit. Typically, everything before the instruction issuer, we call that part front end, and everything after the instruction issuer, we call that part back end. So the instruction issuer will find instructions from the wavefront pools and launch those instructions to the execution unit. Note that the granularity that the instruction issuer issues is at the wavefront level, not each thread level. So every time we issue one instruction, it is for the whole wavefront. Then there may be 64 operations that need to complete it by the execution unit. So what is the rule that the instruction issuer issues instructions? How the instruction issuer determines which instruction can be executed? So there are some rules. First, the instruction issuer issues every cycle. And in each cycle, the instruction issuers select the wavefront from one wavefront pool. That means the instruction issuer have at most 10 options. That is the number of wavefront slots in each wavefront pool. In the next cycle, the instruction issuer will go to the next wavefront pool to issue instructions from those wavefronts. The second rule is that there can be no two wavefronts or two instructions can go to one unit. One unit can only execute one instruction at a time. So if you issue two instructions into one unit, there will be a conflict and the execution unit is confused. The wavefront must have fetched instructions. The instruction must be ready to be there to be executed. If there's no fetched instructions, the instruction fetcher needs to fetch instructions for that wavefront. Then the wavefront must not be running another instruction. So sometimes we may have some instruction that takes longer time to execute. For example, those very complex instructions like sine, cosine, log instruction may take many cycles to execute. If those instructions are still being executed in the instruction pipeline, we cannot issue an instruction from that wavefront again. So from the perspective of each wavefront, the issue is in order and the completion is also in order. That actually avoids a lot of problem for execution order headers like write after write, write after read, read after write, and this type of problem, because it's one instruction at a time. Because wavefronts are relatively independent from each other, we don't really need to consider the dependency between wavefronts. The only exception is memory instructions. So remember those wait count instructions. Every time we launch one memory instruction, we can execute the next instruction without waiting for the memory to return. Avoiding header is a responsibility of the compiler to insert the wait count instruction to guarantee that the data is ready. But the instruction issuer doesn't really have any logic to resolve data header. Understanding these rules, we can try to summarize this instruction issuing process in another perspective, that is the issue width. How many instructions that we can issue at one cycle. Basically, there are 5 units: the branch unit, scalar unit, vector memory unit, SIMD unit, and LDS. So we can launch 5 instructions per cycle. There is actually another unit called export unit if you look at AMD official document, but we rarely see export instructions for general purpose computing. It's designed for exporting pixel values to the screen. But there is one exception. There are some special instructions. For example, we have wait count, we have barrier, we have end program. Those are considered synchronization instructions and we do not really need to execute. So we don't really need to issue any instructions. Those can be consumed within the wavefront pool. So one of the most special component in the whole compute unit is the SIMD unit. It's where the computational power comes from. So in the next video, we're going to discuss the internal structure of the SIMD unit and see how this SIMD unit can provide the computational power of AMD GPUs.